Last December, this was quiet farmland in rural Indiana. Today, it hosts one of the largest AI data centers on Earth. Close to 1 million AI processors under one roof, pulling up to 2 gigawatts of power. And here's the remarkable part. Inside, there is not a single GPU. This is the first AI supercluster of this scale built without a single GPU. And it's either the smartest bet in modern AI or the most expensive miscalculation in computing history. Welcome to New Carlisle, Indiana, population 1,900 people. A town so small you could walk across it in 20 minutes. Yet today, it hosts Project Rainier, an $11 billion AI supercluster that somehow went from farmland to fully operational in under 12 months. Amazon didn't stumble into Indiana by accident. This was calculated. Vast, affordable land, space to expand far beyond what exists today, and most importantly, access to a power grid that can deliver more than 2 gigawatts of electricity. That's enough to power a city of millions. Right now, the largest tech companies on the planet are locked in a race to control AI infrastructure itself. Not just the models, but the physical foundation these models run on. Hundreds of AI clusters are rising across the United States, Europe, and Asia. Almost all of them follow the same formula: endless rows of GPUs. Take the world's biggest AI supercluster today, xAI's Colossus 2 in Memphis. It runs close to 1 million NVIDIA Hopper and Blackwell GPUs under one roof. This model is powerful and proven, but Project Rainier breaks that pattern completely. What makes it fundamentally different is what sits inside. Instead of filling rooms with GPUs, Amazon built the system around its own custom-designed chips called Trainium. And that decision changed everything economically, technically, and strategically. Until now, the rules were simple. Buy GPUs, scale, repeat. The more you buy, the more you save. But explosive demand made GPUs the primary constraint. Manufacturing delays started piling up. The bottleneck shifted from chip production to something most people never heard of: packaging. Blackwell GPUs rely on TSMC's advanced packaging technology called CoWoS-L. This packaging tightly integrates high-bandwidth memory directly with the GPU on a single massive interposer. Its single packaging step has quietly become the true choke point of the AI supply chain. Lead times stretched into months. Costs climbed, and not just for the chips, but for everything around them. When a single high-end rack can approach $3 million, you can imagine what it means to fill an entire data center with thousands of them. Many still think NVIDIA is selling GPUs. In reality, they control an entire ecosystem: server platforms, networking solutions, enterprise software. Big tech companies were no longer simply buying compute. They were buying into a controlled ecosystem. At the same time, workloads kept exploding. Models jumped from billions to tens of trillions of parameters. Training cycles stretched across many months. Power demand climbed into the gigawatt range. Suddenly, performance alone was not the main constraint. Cost and efficiency became just as critical as raw compute. Amazon saw this early. Even at their scale, they did not control their own AI infrastructure. So the strategy had to change. Amazon decided to build its own silicon, an ASIC, application-specific integrated circuit, built specifically for the month-long process of training large language models. This is the beauty of ASICs. You can take the core-defining algorithm and literally engrave it in silicon. That unlocks efficiency, which software can merely imitate. Inside Trainium 2, you don't find countless small GPU-style cores. You find a large number of neuron cores wrapped in high-bandwidth memory. 2 compute dice, 4 stacks of high-bandwidth memory, advanced CoWoS-R packaging. All of it optimized for cost efficiency and a smooth supply chain. According to Amazon, this setup delivers roughly 50% better pricing than comparable GPU-based systems. Plus, this custom solution can reduce data center energy consumption by up to 40%. The objective is not to outmuscle GPUs on raw performance. The objective is more strategic. Control the infrastructure, tame the cost curve, and dictate the economics. Just a few days ago at Amazon's re:Invent event, they announced Trainium 3, built on a 3-nanometer process. 4.4 times more compute, 3.9 times the memory bandwidth, and 5 times more AI tokens per megawatt of power. That last number is critical because at this scale, power is everything. When you build an AI data center, you're not just stacking servers. You're orchestrating power lines, substations, on-site generation, cooling loops, transformers, and grid stability. When fully built, Project Rainier is expected to draw more than 2 gigawatts of power. In a town of just 1,900 people, one AI campus now rivals the power appetite of an entire region with millions of homes. The local grid was never designed for a machine of this magnitude. The problem is not even the scale, but stability. Traditional data centers were built around storage and routine compute. AI data centers are a different beast. GPUs don't draw power smoothly. They demand it in jumps, up and down in milliseconds. If the supply cannot keep up with these swings, the entire system becomes unstable. A sudden surge can drop voltage, and in the worst case, ripple through entire training runs. Restarting those runs burns millions of dollars in wasted compute. Amazon had to reinvent how power flows in a data center. At Rainier, they deployed a large-scale battery system to absorb power fluctuations. Batteries store energy when demand is low and release it instantly when demand surges. The result is calm, predictable power feeding hundreds of thousands of AI chips without interruption. Hyperscalers are no longer just building data centers. They're literally turning into energy developers. Amazon is funding power plants, reinforcing grids, investing in renewables, all to lock in cheap, reliable electricity before anyone else gets there first. In Pennsylvania, Amazon acquired a 960-megawatt data center campus right next to a nuclear power plant. The data center is connected straight to the power plant, giving Amazon access to almost 40% of all the electricity the plant produces. Securing 2 gigawatts of power only unlocks the next problem. The moment electricity hits the servers, it becomes heat. 2 gigawatts of heat wrapped inside 4 walls. To cool a data center at this scale normally takes millions of gallons of water every day. In extreme cases, it pulls from the same water supply people rely on for drinking. Project Rainier stepped straight into that pressure point. Amazon took a different path. They designed Rainier to minimize water use as much as possible. From October to March, it uses no water for cooling at all. In warmer months, water is only used for a few hours per day on average. To make this work, Rainier relies on massive fan walls and relentless airflow. The system stays in constant motion. But this choice carries consequences. More noise, more power draw, more strain on the electrical system. Water is roughly 30% more efficient than air at absorbing and moving heat. This design reflects a calculated compromise, a core dilemma at the heart of modern AI. Protect water but burn more power, or save energy but strain local water systems. Every decision here carries a cost. Even with the best silicon and cooling, there's one thing that decides everything: the network. Unlike data centers built around NVIDIA's infrastructure, which lean heavily on optical networking, Amazon chose a different path. They built a custom network based on dense copper wiring. Optical interconnects at this scale are extremely powerful, allowing for higher bandwidth and more elegant layouts, but they're also extremely expensive. Amazon went with copper for practical reasons. It's cheaper, more familiar, easier to install, and deeply embedded in existing infrastructure. But copper comes with consequences. AI data centers push toward extreme bandwidth, 800 gigabits per second and moving toward a terabit per second. Copper runs into hard physical limits. What used to work over long distances now only works over a few feet. Suddenly, physics pushes back and generates loss and heat. Amazon stayed with copper, only partially introducing optics for longer distances, and paired it with aggressive cooling techniques and obsessively controlled layouts. The result works, but at the edge where every inch of routing matters. This scale of investment only makes sense when you have an anchor customer, someone who will truly benefit from that much compute. Microsoft has OpenAI. Amazon's anchor customer is Anthropic. Their Claude Opus 4.5 model is one of the best in the world. Their revenue is growing fivefold, approaching $5 billion annually. Amazon has invested roughly $8 billion in Anthropic. And Anthropic has committed to running its flagship models on Amazon's Trainium chips. If you're using any of Claude's latest generation models, that traffic is running on Trainium. Amazon claims they've already deployed over 1 million Trainium chips to date, and they got to 1 million chips in record speed because they control the whole stack. What's interesting is that Trainium 3 was co-designed in close collaboration with Anthropic's team. In practice, their model architecture shapes the silicon. The silicon, in turn, accelerates the models. This is the true edge of co-design, unlocking efficiency that general systems can never reach. Until recently, this level of co-design was almost exclusive to Google and DeepMind through TPU, Google's tensor processing unit. Gemini, one of the best models on the planet, runs on Google Cloud powered by these chips. And now everyone wants them. xAI and Meta are circling. Anthropic is placing massive TPU orders. Why are all the top AI labs lining up for these chips? Because GPUs are designed for versatility. Their power is flexibility and raw peak performance. Trainium and Google's TPU sacrifice versatility to maximize efficiency. Currently, everyone cares less about benchmarks and more about one brutal metric: performance per dollar. Rainier is part of a much larger build-out. Amazon is committing another $15 billion to Indiana alone, meaning more land and over 2.4 gigawatts of new capacity. Across the United States, Amazon is investing over $100 billion in AI infrastructure in 2025 alone. These new sites will power enterprises and AI labs running at industrial intensity. Some will run on Trainium chips. Other sites will load up on GPUs for flexibility and immediate demand. Amazon runs both tracks in parallel because they're not betting on a single future. They're letting the market decide which one survives. Everyone is talking about an AI bubble, but the real problem is structural. Anthropic spends heavily on Amazon Cloud. Google also invested another $4.5 billion in Anthropic, and Claude now runs across both ecosystems. Amazon Trainium chips and Google TPU infrastructure. It's a capital loop. Big tech injects money into AI labs. AI labs spend it on compute. New models need more compute, driving even more chip sales. The danger is that this cycle repeats faster than actual profits can catch up. The story is not just about building better chips. It's about control over the most scarce resource in AI infrastructure: power. Amazon's strategy is clear. At first, they aim to build more efficient chips. But the real strategy is full vertical control. Chips, software, data centers, energy sourcing, and renewables. Ohio, Mississippi, Pennsylvania, new sites keep switching on. These are not just data centers. This is a distributed power grid spanning the entire United States. The future winners in AI will not just be the ones with the smartest models. It will be the ones who secured power, land, and silicon first, and aligned them together in one system that can scale without becoming too expensive to sustain. AI hardware is no longer a one-vendor story. Meta is designing chips with help from Broadcom. Microsoft is following the same path. AMD is closing the performance gap. We constantly see a wave of new AI accelerators being announced, and just as quietly, many disappear. Not because the idea is wrong, but because the bar is too high. If you cannot build a system meaningfully faster, cheaper, and more efficient than what you can already buy off the shelf, why build it at all? Tesla Dojo is one example. Beautiful moonshot, years of work, world-class team. Yet this year, it was shut down. Startup GraphCore burned $700 million building custom AI silicon, betting on the wrong algorithm. Across the planet, farmland is giving way to data centers. Cornfields are becoming compute fields. Land once measured in harvests is now measured in gigawatts and exaflops. 10,000 years ago, the first great revolution taught humans how to feed ourselves. This one is teaching us how to feed machines. And everything that follows will depend on that choice. If you have any questions, write it in the details section. Like and subscribe for upcoming AI content, then watch the next AI video that will appear in front of you.